Welcome to 102C on Monte Carlo methods. My name is Yingnian Wu, and my email is ywu@stat.ucla.edu. Currently, I set my office hour on Tuesday and Thursday, 4 to 5 p.m., right after the class. And for this course, we have weekly homework, and also we have a final exam on the last day of the lecture. Okay, so about this course, we are going to cover the following topics. So we start from random number generators, and then we shall study Monte Carlo integration, in particular a special case based on the so-called importance sampling. After that, we shall study a very important class for Monte Carlo method called Markov-Chain Monte Carlo, or MCMC. So if we have time, we shall also briefly study genetic algorithm and particle swarm algorithm for optimization. So just a little bit background on Monte Carlo methods. So this class for methods was invented in 1940s during the Second World War, and US had the so-called Manhattan Project to build the atomic bombs. And at that time, the first computers were also constructed, and Monte Carlo methods were implemented on those computers to do some computations that are related to this atomic bomb project. So the following are some key players. So Fermi was a theoretical physicist who got Nobel Prize on I think his theoretical work mainly, but he's also a experimentalist, which is extremely rare. And in particular, he studied this chain reaction, where he need to calculate quantities that related to the so-called neutron diffusion. So it is very difficult to compute those quantities using a deterministic numerical methods. So Fermi then came up with the idea of using random sampling, or using the randomness to do the approximated calculations. And later, Ulam, who's a applied mathematician, and Van Neumann, who was a polymath, who has done a lot of important work in different areas. So they also came up with this idea of using a random sampling to do the calculations in neutron diffusion in this Manhattan Project. So at that time, they need a code name for the method. So Metropolis, who was actually responsible for one of the first generation of the computers, the MANIAC, he proposed the name Monte Carlo. So Monte Carlo is actually a European version for Las Vegas. You know, it's a gambling city where people go there to do gambling. And Metropolis often heard Ulam complaining that his uncle borrowed money again and went to Monte Carlo to do the gambling. And so, you know, this gambling is based on this randomness or random sampling. So that's why Metropolis proposed this code name, Monte Carlo, for this sampling-based method. And later, Metropolis was also involved in the invention of the so-called Metropolis algorithm. So that's actually after the Manhattan Project, immediately after the Manhattan Project. So people developed this Metropolis algorithm. So it was ranked as the top, or the number one most important algorithm in scientific computing in 2000 by a panel for experts on computing. So this also underlies the importance for Monte Carlo methods in general. Okay, so now let me briefly motivate why we need Monte Carlo method. Okay, I think I found it. Okay, so why Monte Carlo method? The first application for Monte Carlo methods is to do the simulation, because a lot of processes are actually called stochastic processes, which means they are random processes. In fact, at the most fundamental level, our universe is essentially random, and it is governed by those laws that compute probabilities. So the wave functions, if you square it, you get the probabilities. And also you have heard of uncertainty principle. So therefore, the probability is really everywhere, underlies a lot of different processes in nature. And even if you have everything deterministic, if you study a system, for example, a cup of water that consists of 10 to the 23 molecules, you also need to use some probabilistic modeling in order to study some statistical properties of the system, for example, temperature or pressure. And in estimating those statistical properties, you need to simulate the system, the evolution of the system. And we have to insert randomness in our simulation. And that's why we need Monte Carlo methods. And when we simulate those processes, we often want to calculate some quantities, for example, some probabilities or some expectations, which is the long run average. And so those probabilities and expectations can be expressed as integrals. So that is Monte Carlo method is actually very, very important for approximating the integration. Even if there's no probability whatsoever, for example, suppose we want to calculate the integral for f of x dx from 0 to 1. So this is essentially its area under the curve. So if we cannot get analytical solution or analytical answer in closed form, then we can use numerical method. So that is, we can divide the range from 0 to 1 into equally spaced bins. And then we approximate the integral of the area under the curve as a summation of those the area of those rectangle bins, which can be written as summation of x, where this time we discretize x as a equally spaced points from 0 to 1, and then we sum over fx delta x, where delta x is the size of the bin, and the height is fx times the base delta x. We get the area of this small rectangle. We sum them over, and if delta x become very, very small, then we get this integral. Okay, in fact, this is how the integral is defined as a limit for the summation of the areas as delta x approaches 0. So this is a one-dimensional situation. But in the two-dimensional situation, if we continue to divide the range, then we need to divide both the range of x1 and the range of x2 into those equally spaced bins if we want to compute this two-dimensional integral. So that is, we have two variables, x1, x2, and we have a two-dimensional function f of x1, x2. For example, x1 squared plus sine x2, I just make up an arbitrary function, and you want to compute this double integral. And again, for numerical integration, you can divide this range of interval from 0 to 1 on x1 into, say, n capital N bins, and also the range for from 0 to 1 on x2 into capital N bins. So this together give you n square cells, and then you just sum over all these n square cells for this integral. So this type of discretization can be generalized to higher dimension, For example, in the d-dimensional situation, suppose we have variables x1, x2 to xd. So they are all within the range from 0 to 1. And we want to compute the integral of this multivariate function over this d-dimensional cube, where d stands for dimension. And if we continue to divide each dimension into n equally spaced bins, then we have n to the power d cells. So for numerical integration, we need to sum over this n to the power d cells. But consider that if we want to get a very accurate result, we need n to be very big. And if d is also very high in the high dimensional situation, then n to the power d can be an extremely big number. So there's no way for us to go through all this n to the power d cells. So in that case, then this numerical deterministic method breaks down. So they just are not feasible at all in the high dimensional situation. And this is called curse of dimensionality. However, we can do random sampling. So that is, instead of summing over all this n to the power d cells, we can just randomly sample a small number of cells from this n to the power d cells. So this is essence of Monte Carlo method. So we have a large population of cells. This number is just too big. For example, if n is 1,000, d is 100, then we have 1,000 to the power of 100 cells. This number is simply too big to enumerate. And then what we do is we may just randomly sample 10,000 cells from this n to the d cells. And if n is very big, then each cell is very, very small, almost like a point. And in that case, you can still just sample, say, 10,000 small cells, or rather 10,000 points in this d-dimensional cube. And that's the Monte Carlo method. So here, n, small n, is, say, 10,000. We sample 10,000 points. So this should be a comma, comma here. So those are, it's not a product, okay? So those are just 10,000 points sampled equally likely from this d-dimensional cube. We use 0 to 1 to the power d to denote this d-dimensional cube. So you just randomly sample n small n equals 10,000 points in this d-dimensional cube. And then you can approximate this integral, which is a summation over n to the power d cells by this sample average. So that is, we sum over the f values for all those 10,000 points. And then we divide this by n, 10,000, we get the average. So the average of the f values on this of this 10,000 points. So this is a Monte Carlo estimate of this d-dimensional integral. Okay, and so here just a little bit notation. So each capital X is a point in this d-dimensional cube. Okay, so that it has a d coordinates, and x1, x2 to xd. So, and then we sample n points from this d-dimensional cube, and we compute the average of their function values. This gave us a approximation, Monte Carlo approximation. Because we do random sampling, so this average has randomness, but we can show that the variance of this randomness goes down as we increase this small n. And in fact, the variance is inverse proportional to the sample size, small n. So this example actually captures the essence of the Monte Carlo method. Okay, let me move it here. So that is, we have a big population, in this case, n to the power d cells. For example, n is 1,000. We divide each dimension into 1,000 bins, and d is 100. So this is a very big number. So there's no way for us to sum over all those cells. We cannot even enumerate them. It will take, however, to enumerate so many cells. And what we do is we get a random sample for n points. Say n is 200. We get 200 points, and we compute the average. So this actually remind us for the election, right? So on the election day, those hundreds of millions people will vote, but before the election, we cannot afford to go through all the people, but we can randomly call, say, 1,000 people from this population voters. And then based on the sample proportion, we can get a sense of the population proportion of those voters who will vote for a particular candidate. Okay, so this is just like a survey sampling. So instead of going over the whole big population, we get a small random sample, and then we can use the sample average to approximate the population average, and we can use the sample proportion to approximate the population proportion. So this is the whole point of Monte Carlo method. It makes computation feasible, and it actually also avoids the curse of dimensionality, because the variance for the sample average or sample proportion is inverse proportional to this n, but it has nothing to do with d. So however large d is, so here d is 100, even if d is 1 million, it doesn't matter. So the variance is still just inverse proportional to n, has nothing to do with d. So therefore, the Monte Carlo method avoid curse of dimensionality. There is some irony here, because supposedly when we do random sampling, we have randomness, right? But in this situation, the random sampling or the computation based on randomness is only feasible method, and it is actually the most accurate method that we can devise. So that's for integration. And the third application of Monte Carlo method is optimization. So the idea is that the optimization is closely linked to simulation or random sampling. For example, in statistical physics and also in machine learning, we often study a probability distribution in this form, where we use pi to denote a probability distribution, and x is a configuration of a certain system. X may consist of multiple components or multiple elements. And then the distribution is in the form of 1 over z e to the power negative ex divided by t. So here E of x is energy of the system, and t is the temperature, and z is a normalizing constant. So that is the summation of this thing over all possible x, so that this probability distribution sum to 1. It is a legitimate probability distribution. So the idea is that if for a particular figure x, a configuration x, if the energy is small, then the probability is high, which means it is more stable. So that's the so-called Gibbs distribution or Boltzmann distribution. And we can consider that if we draw fair samples from pi of x, then only those configurations with low energy will be sampled. And so therefore, it is like when we do the sampling or simulation, we are actually minimizing this energy. And in particular, if we decrease the temperature, then the difference in the energy will be magnified. So only those configurations with the lowest energy will have a certain probability of being sampled. So therefore, if you sample this distribution at the low temperature T, and then the sampled configuration automatically has a low energy, which means you are actually doing energy minimization. And the idea of simulated annealing is actually based on this idea. That is, we keep sampling from this distribution, and we gradually reduce this temperature T. So eventually, we are going to sample this point, which is a global minimum for the energy function. So this simulated annealing can be used to solve very difficult optimization problem. For example, the traveling salesman problem, where it hopefully eventually will converge to the shortest path, which we define the distance or the length of the path as our energy. Then we minimize this energy to get the shortest path. So we shall study this this method later on when we study Markov-Chain Monte Carlo. So here I just want to give you some teaser or a taste for this optimization. And also Monte Carlo methods are very useful in artificial intelligence, machine learning, in particular deep learning. So when we train a neural network in the deep learning, often we use the so-called stochastic gradient descent algorithm, where the gradient is computed by the backpropagation. And the stochastic means that we compute the gradient only for a mini batch that is randomly sampled from the big training data set, which consists of a huge number of examples. Okay, and certainly that involves some randomness. That's why it is called a stochastic gradient descent, because the gradient is computed over a mini batch randomly sampled from the training data. And also we have the so-called generative model. It's not generate, but generative models, so that we can generate different, for example, faces or images. We can also generate speech. So those are called generative models, and the generation involves randomness. So actually we are randomly sampling from a certain probability model. And also in AlphaGo, we choose the next move based on Monte Carlo tree search. So that is for the game tree can be in the Go, the game tree can be very broad, the breadth can be very big, and the depth can also be very big. So the game tree is huge. We cannot go over the whole game tree in order to solve this game, but we can sample those promising branches which correspond to the moves by the top experts. And then now we can decide which move gave us a win. So that's the Monte Carlo tree search. That is, we randomly sample some of the moves so that we get certain branches, those promising or reasonable branches to decide the next move. So these are the applications for Monte Carlo methods. So we shall study those methods more carefully later on. So here I just give you a brief introduction. And let me then move on to, let's see, we go to the next page. Okay. So now let's start the real business. So we are going to study the first part of this course on random number generators, because whenever you use Monte Carlo method to do random sampling, you have to start from random number generators. And all the randomness in the modern computers start from this so-called uniform random number, or unif from 0 to 1. So that is on this interval, right? We randomly sample point on this interval, or you can imagine randomly throw point on this interval, and all the points on this interval are equally likely. So you can imagine that all the points on this interval form a population, which is uncountably infinite many points, right? And you just randomly sample point. So all the points, they have the same probabilities of being sampled. And we want to do this repeatedly, which means we sample U1, U2, and UT, and so on from this probability distribution. And we do this independently. So later I will be more careful about what we mean by independence. But the point is that if you get a sequence for those uniform random numbers, you can see what's the consequence. So you can do a scatter plot of those numbers so that each number is a point on the interval from 0 to 1. And then you will see that those points are evenly spaced, not exactly evenly spaced, because those are the random samples. There's a randomness, right? They are roughly equally spaced. But certainly, if you look at this, these examples, they are not equally spaced. You have more points here than the points here. And for this one, you have more points here than here, right? So that you can actually see that by plotting a histogram. So that is, you divide the interval from 0 to 1 into those equally spaced small bins. And then you can collect those points into those bins if the points fall into this small interval. And then if you do a histogram, the histogram should be more or less uniform. So there's a statistical fluctuation because randomness is introduced by random sampling. But if the sample is big enough, so that is number of points is very big, then you should have a more or less uniform histogram. But for that one, you may have a histogram like this, which is certainly not uniform. And also, when we say that U1, U2 are independent of any adjacent pair of random numbers are independent, what do we mean? So, for example, if I say we sample U1 and U2 independently from this interval from 0 to 1. So here independence means that if you look at suppose this is the direction of ut, and this is the dimension of ut plus 1. And then you can imagine that ut and ut plus 1 become the coordinates of a two-dimensional point. This two-dimensional point is within this unit square. And independence means that this point has a uniform distribution over this unit square. Okay, so that is if you plot ut and ut plus 1, so that each point is a ut plus 1. For example, this may be u1, u2, and this may be u2, u3, and this may be u3, u4. So each pair, right, become the coordinates of a two-dimensional point. And then you will see roughly equally distributed points. You want to see the situation like this, so that those points lie on certain lines or curves. So that will not be a independent pair. So ut and ut plus 1 are not independent in that case. So here independence in this uniform setting, it just means that all the points in this unit square has equal chance of being sampled. So that's the idea of independence. And this actually in a infamous example of Randall. So IBM released a Randall random number generator, and the random number generator actually has some pattern like this, which suggests that they are not independent at all. So it was lucky that people didn't use that code to do the neutron diffusion type of calculations, which has very big consequences. Okay, and then what about the U1, U2, U3, or in general ut plus 1, ut plus 2? And then you can think of this as a three coordinates of a three-dimensional points. The three-dimensional points is in the three-dimensional cube. And if ut plus 1, ut plus 2 are independent, that means this is a random point in this unit cube. So every point has equal chance of being sampled. And if you plot u1, u2, u3, u2, u3, u4, and so on, so each one is a point in this three-dimensional cube, right? And you see the uniform distribution of those points. So that suggests that ut plus 1, ut plus 2 are independent. So that's what we mean by independent samples. Okay, so how do we sample or generate random numbers in our computer? So in the computer, we use the so-called linear congruential method to generate random numbers. So we start from an integer x0, and we call this as our seed for the random number generator. And then we iterate the following process, so that we start from 0, and then we iterate xt plus 1 equal to a times xt plus b. So that's a linear transformation. And then mod m, so this is congruential. And those a, b, and m are very carefully chosen integers based on number theory. For example, we can choose a equal to 7 to the power 5, b equal to 0, m equal to 2 to the 31 minus 1. This is a special type for prime number. Okay, and then we can just keep iterating this this relationship, right? This iterative algorithm, and then we generate x1, x2, x3, and so on. And here, what do we mean by mod m? So the idea is that after we compute this linear transformation, which is a big integer, right? We then divide this by m, and we take the remainder. For example, if we divide 7 by 5, and then the remainder is 2, right? So in that case, if we divide this number by m, we take the remainder. So the remainder can only be 0, 1, 2, and m minus 1. So that is, if you choose a, b, and m very carefully, then the xt can be considered as a random number from 0, 1, 2, and m minus 1. So if m is big enough, and if we let ut to be xt divided by m, then xt divided by m is a number from 0 to 1. And if m is big enough, we can treat this ratio as a real number. And then we can use a mathematical idealization to think of this u sub t, which is xt divided by m, to be a uniform random number, which is a real number. Okay, so that's a random number generator. And here, even though this ut is a fraction, it's a rational number, but if m is large, so just by mathematical idealization, we just treat ut as a continuous, a real number. Okay, and then we generate random numbers from 0 to 1. Okay, so let me move to the next page. So let's go over one example. So suppose we start from x0 equals 1 and xt plus 1 equal to 5 times xt plus 0 mod 7. And then x1 equal to 5 times 1 plus 0 mod 7 is 5. And if you keep doing this calculation, you get the 4, 6, 2, 3, 1. And then it repeats itself, right? Because x0 is 1. So it starts to repeat itself. So you can see that this code is actually a deterministic computer code, and eventually it repeats itself. So therefore, there's nothing random, and it is actually pseudo-random because everything is deterministic. However, for all practical purposes, we can consider this to be a random number in the sense that if you use this to open a casino, you are not going to lose money if you keep it secret, the number A, B, M, and also the seed. Okay, so that is, it is very difficult to find the pattern in the sequence of data. So if you cannot find any pattern, then you may as well treat this sequence as a sequence of random numbers. After you generate a uniform random number from 0 to 1, and then you can generate other random numbers, and then you can simulate any stochastic processes. And actually, there is a very general method called the inversion method, so that we can generate any other random variables for whatever distributions, probability distributions, using this inversion method. The simplest example, for example, we want to generate a fair coin, and then we can generate uniform random number u from 0 to 1, and then we let x to be head if u is bigger than or equal to 1/2, and let x be tail if u is less than 1/2. So later I will explain why it is called the inversion method. But if we want to generate a fair die, we can also generate u from uniform 0 to 1, and then we divide the range from 0 to 1 into 6 equally spaced intervals. And then we randomly throw a point into this interval, which means we generate u from uniform 0 to 1. And depending on where you fall into, which interval it belongs to, we then return the corresponding number. This gives us a fair die. And we can generalize this method to generate any probability distributions, including both discrete and continuous distributions. So we shall study this inversion method in detail in our next lecture.